we're now going to use implicit differentiation to find the slope of a tangent line on a curve where we cannot necessarily solve the equation of the curve as for y as a function of x. Okay, the circle, we could do that. We had the top semicircle and the bottom semicircle, and so we could have used the old technique to find the derivative. But for this one, you have x cubed plus y cubed is equal to 9x times y. There's no way I can get y by itself. You could try here, but you're not going to be able to solve for y. But still, what I'd like to do is I'd like to get the slope of the line tangent to this curve. So this is actually the curve. It's kind of an interesting curve. It's a loop that goes around like that. And I want the slope of the line tangent to the curve right there at 4, 2. So we're going to use implicit differentiation to do that. So, and this will show you why implicit differentiation is so useful, because this is not something we could have done using regular differentiation. So there's my equation. So now I'm going to take the derivative of both sides with respect to x. Okay, so this side here, the first term is just 3x squared. And the second term, we're going to treat y as if it's inside a cubic function. So we're going to do the derivative of the outside function evaluated at y times the derivative of the inside function, which would just be dy dx. Y is the inside function. It's an implicit function of x. Okay, so that's the left-hand side. So now this right-hand side, notice we have we can think of this as 9x times y. And that's like the product of two functions. So what I have to do is I have to use the product rule on this. So I'll treat 9x as the first function. So if I take the derivative of 9x, I would just get 9 times y plus the 9x, the function, the first function, times the derivative of y, which is just dy dx. Okay, so it would look like this. So now what I got to do is I got to solve for dy dx. And the way I do that is I bring all the terms over that have a dy dx over to one side, and then all the terms without a dy dx to the other side. So in doing that here, I get this. So I'm going to bring this over. And then I'm going to bring this is 9y, I'm going to bring the 3x over to this side. So now I have this, and the reason for doing this is I can factor out the dy dx, and then I'm left with just 3y squared minus 9x. And so what I can do is I can divide both sides by this, leaving me with just dy dx, and I get 9y minus 3x squared over 3y squared minus 9x. And so this would be an expression for the derivative of the curve, the slope of the tangent line, and it's an expression involving x and y. And so what I want to do is I want to find the slope of the line tangent to the curve here at 4, 2. So I got an x and a y. Okay, I got an ordered pair. So I want to find dy dx there at 4, 2. So what I'm going to do is plug in 4 for x and 2 for y. So this would be 9 times 2 minus 3 times 4 squared divided by 3 times 2 squared minus 9 times 4. So I would get this, and now I get, this is 18 minus, so 4 squared would be 16 times 3. So 16 times 3 would be 30, 18, 48. And then here you get 4 times 3, that's 12 minus 36. Okay, so this would be negative 30, and this would be negative 24. And now there's a common factor of 3. The negatives cancel out. Common factor of 6, actually. So that would be 5/4. And so that would be the slope of this tangent line, 5/4. Okay? And so there you go. We can use implicit differentiation to find the slope of the line to even these really strange, interesting curves that are kind of fun. And so the technique is the same. The strategy here, you take the derivative of both sides, and then you got to solve for dy dx. This usually involves bringing all the terms with a dy dx to one side, all the terms without one to the other side, so then you can factor out the dy dx and divide by what remains there inside the parentheses, and then you get this derivative. On this assignment, you'll have a lot of interesting equations like this, and you won't have a clue what they look like. So if you're curious what these look like, I encourage you to use Desmos. You can type these go to Desmos, type these in, and Desmos can graph these equations, no problem. It's not something you can do with this calculator, so there's no way I could have gotten this in this calculator, not at this point here, because I can't solve this. Y is a excuse me, I can't solve y as a function of x here. Excuse me. So Desmos would be a way to actually get a picture of the curve, okay, to see if what you're doing and see if your final answer actually makes sense. So in the next video, what we're going to do is I'll show you several other examples of just finding the derivative function, not actually plugging in a value here, but actually finding the derivative function just to see how the implicit differentiation works. And then we'll do some couple problems where we find tangent lines and also normal lines. So a normal line is just a line that's perpendicular to the tangent line. Okay. That's known as the normal line of the function. And so that's where we're headed with all this.